Open the Hello everyone, and welcome to our yet another series on machine learning. This is the introduction to advanced ML series, and thank you for joining us today. My name is Sneha. I am a data scientist at a medical device company here in San Diego, and I'll be leading the session today. I am excited to introduce to you some new concepts for the next 2 hours. But before we begin, let's start with some announcements. First and foremost, a huge thank you to our amazing team of volunteers for putting together this series. Everyone has built amazing content that we can't wait to share. Our volunteers and leaders are present in our panelists on this webinar. For the first session, I'll be the speaker, and all the others are present on chat to support you. Feel free to reach out to any of us with any questions you might have. Next, I would also like to thank our sponsors, Home Depot, for putting together much needed events for our community. Do show your appreciation for them by retweeting our posts. The post will be shared in the chat as well. And last checkup before we begin the session. These slides are present at this URL mentioned here. One of our panelists will share the information in the chat. Feel free to download and follow along with us. If you have any questions regarding today's session, post them in the Q&A section. Our panelists will again respond to your questions during the course of this session. If you're facing any issues, respond to your questions during the course of the session. So, if you're facing any issues during this webinar, do reach out directly with the panelists so one of us could help you out. Finally, don't forget to follow us on LinkedIn and join our Slack channel for interesting contents and up-to-date data science events. Our panelists will share this information in the chat as well. To kick off this series, as mentioned, it is a 6-week series starting with K nearest neighbors. And here's what we have in store for the upcoming sessions. The registration link is the same for all these sessions. So if you're on this webinar, you have registered for all the sessions and you are all set. Today, we'll be talking about K nearest neighbors. The session will follow this flow. We will start with a simple introduction to KNN and then talk about the intuition behind the model, why it is so popular, and why it is a simple classification algorithm. Following that, we will try solving a problem manually in Excel, where you will understand the math involved and the calculations behind the classification model. But don't worry, we'll take the easy route. That will be the first hour of this session. After that, in the second half, it is a code with me where we will have a Google Colab notebook, and I will walk you through the entire process from setting up the Colab notebook, getting the desired data, analyzing the data, and then building and evaluating your very own KNN model. That's not it. We will end the session by talking about the next steps on what you can do to kickstart your own project. Some ideas on that as well. So let's start by answering a simple question. What is K nearest neighbor? There's this famous quote which reads, "You are who you surround yourself with." Today, we are going to look at the ML algorithm that represents this as the base. To put it simple, the algorithm is based on the concept that similar cases with the similar class labels are always near each other. So if there is a new incoming point, we know that it should belong to the similar class labels that are surrounding it, aka the neighbors. KNN is one of the basic yet essential classification algorithms in ML. It belongs to the supervised machine learning domain and finds intense application with pattern recognition to classify the incoming data points. It uses distance metrics, also known as feature similarity, to predict the outcomes. A simple definition states that KNN finds similar data points in the data, and it makes an educated guess to classify a new incoming data point. Let's look at a real life example. Let's suppose you're going back to school and you're on your first day of class and you're trying to make friends. You start to socialize, and then you realize you connect with the people who share your same thinking, interests, and hobbies. Thus, thinking, interest, and hobby are the features, and is that person going to be your friend or not is the classification that we'll be making. I hope this is analogous to show you how KNN works. Now let's reiterate the definition again. There are two classes in our image here. You can see that it is a binary classification problem. There's class A, which are the small yellow triangles present on the top of the plot, and class B, which are these small blue circles that are present in the bottom. And now there is a new point that is coming in. The KNN model stores the vector positions of these data points in the training data set. And when a new data point enters, it measures the distance between the new point and all the other data points. Once this distance is calculated between this new point and all the other data points, we then choose an arbitrary number, k, to determine the neighbors. So this is where the k in k nearest neighbors mean. When considering more than one neighbor, we use voting to assign a label. For example, here I'm saying the k is equal to 3, which means I'm going to look at 3 closest neighbors to the new point. And we can see, we can count how many neighbors belong to class A and how many neighbors belong to class B. And then we can predict the outcome as the class that is more frequent. Here, in other words, the majority class among the k nearest neighbors. The example shows that the new point would be classified as class B because of majority voting of class B having 2 and class A having only 1 vote. Now, to put everything together again, we can explain this algorithm in 4 simple steps. It starts by placing the unknown value, say x, with the other data points in the data set. In a 2-dimensional space, you can say a point can have an x value of 2 and a y value of 5. Now, the KNN takes an appropriate value of k. When we start, it is an arbitrary number, but while applying KNN, this value is usually provided by the user. And then it should be optimized to find the best model. We'll be finding the optimal value of k in the hyperparameter tuning part of the presentation. In the last example, we use the value of k to be 3. In step 3, we start calculating the distance of the incoming data point from all the points that are present in the vector already. There are various distance metrics that are involved, and this is the second parameter that we'll tune to get the best model. Now, we assign a class or a label, and that's the 4th step to this new data point, which is the majority of the k nearest points we just calculated. In the previous example, the result was the new point was predicted as class B. Now, before we dive deeper, let's see where to use KNN. KNN method has the advantage that they are easy to implement. They are often preferred in the industry because they are simple algorithm. But there are some prerequisites that we need to understand to get high accurate outcomes. The first is we need high quality data that is very highly accurate with less or no missing values. If there are missing values, It is easier to eliminate those data points than compromise on the accuracy of the data. Secondly, sufficient domain knowledge is needed to select the appropriate measure or feature to train the data. The model is very sensitive that any irrelevant feature can bring down the accuracy of the model. So when you build a model, you should make sure that you understand the features and you know those are the exact features that you need to determine the class of the new incoming data point. Lastly, when you don't want to worry about the distribution of data, this is the best model to have. It is widely disposable in real life scenarios since there is no parameter attached to the data. That is, it does not make any underlying assumptions about the distribution of data. Now let's talk a little bit more on the advantages of using this algorithm. As we said, it is a simple classification algorithm that takes a bunch of labeled points and uses them to learn how to label the new incoming data point. Because of the low calculation time during training, the training phase is very cost effective and time effective. The other point is it is easy to interpret. As the model is based on a mathematical formula of distance metric, it is easy to explain when you achieve a result to say why you achieved that result. Again, no underlying assumptions about the data is needed, which is a big advantage because despite that, it usually has high predictive power in outputting the desired results. Hence, it is one of the most sought after classification algorithm in the industry. Now, with all this, we should look at a few disadvantages of the model as well. So we said it is very cost effective in the training phase, but it is the total opposite in the testing phase. So KNN is computationally expensive in the testing phase as it searches the nearest neighbors for the new point by comparing it to all the data points in the training phase. They do not simplify the distribution of objects. Instead, the training set is retained in its entirety. This slows the testing and prediction phase of the training set, of the testing set if the training set has many data points. The most serious shortcoming of KNN is that they are very sensitive to the presence of irrelevant data. Adding a single parameter that has a random value can cause the method to fail miserably. And the last point is that the algorithm works primarily on numerical variables. So if your data set contains categorical variables, which is usually the case when we are doing classification, it has to be handled specially to apply this algorithm. Usually it can be as simple as a label encoder, but sometimes it can be a complex process as well. Now, this is a very simple algorithm, as we said, and we have covered the basis. Let's look at the intuition behind the model in depth. As mentioned already, during the training phase, the model stores the vector positions of all the data points in the training data set. So there is no computation happening here. So that is why it is very effective in terms of time and cost. But when a new data point comes in to predict the class of this new model, so a new point, the model finds the k closest data points in the training data set. Its k nearest neighbors. The testing or prediction phase is when all the computation happens. As we said before, the closest data points are determined by the distance metrics. Now we know that there are two important parameters that we need to tune to get the best model from KNN, the n nearest neighbors and the distance metric. The n neighbors are the number of neighbors to be considered in making prediction and the distance between, yes. So the k nearest neighbors algorithm looks for the closest data point in the data set. The k parameter specifies how many nearest neighbors to consider, and the closeness is defined by the difference between each variable, which is converted to a similarity measure or a distance metric. The distance metric can be computed in a few different ways: Euclidean, Minkowski, and Manhattan. We will elaborate on all of these, but let's first start with n neighbors, or the k value. How do we choose an arbitrary value for k, or how do we optimize k? So as mentioned before, k drastically impacts on the prediction power of the model. In KNN, finding the value of k is not easy. A small value of k means that noise will have a higher influence on the result, and a large value of k makes it computationally expensive. So we need to find what is the optimal value of k that will help us get maximum accuracy, but will not consume a lot of computation. So let's go back to our first example that we classified a new point as class A or class B. Let's say that the value of k that we're considering here is 1. In that case, the easiest choice, or the majority voting, goes to just 1, which is the first little triangle that's really close to the new point. And we know that the prediction is going to be class A. Now, if you look back to when k is equal to 3, we need to consider 2 more close points. So there's this one and the other one. Now you see that the prediction changes because when you take majority voting between class A and class B, the classification is going to say it's a class B. And now let's go a little higher on the k value. Let's say we are going to look at 5 nearest neighbors. Now we have to include 2 more data points here. So I think this one and this one are the closest neighbors. So considering this 5, if we vote, we have 3 from class A and 2 from class B. That suggests that, again, class A wins. Now, how to determine which k is right for us? Let's look at the real value of the class. Sorry. Let's look at the real value of the data point. Here you can see the real value of the new data point is class A, which suggests that k is equal to 1 predicted correctly and k is equal to 5 predicted correctly. That is, they had 100% accuracy, while class k is equal to 3 had 0% accuracy. So this is for a single data point. In real world problems, we have hundreds and hundreds of data points. So we need to take an appropriate value of k, which gives good results to our incoming classification. So to do that, what we do is we take the test set and plot the accuracy or F1 score against the different values of k. Here in this plot, you can see that the overall accuracy, the k values are plotted against the overall accuracy. We see a very high error rate for test set when k is equal to 1. Hence, we can conclude that the model overfits when k is equal to 1. For a higher value of k, we see that the F1 score the accuracy starts to increase, and after a point, it drops. Now we know that at this point, when k is equal to 9, is where we get maximum accuracy of 91%. And this would be the k value that we will want to use if we want to optimize to get the best model of KNN. The next thing to look at is the distance metrics. A distance metric is an objective score that summarizes the relative difference in distance between 2 data points in a problem domain. These distance can be measured with a mathematical formula. So if the distance is small, then it says the elements are similar. And if the distance is large, then the degree of similarity is low. When calculating the distance between 2 points, it is possible that the different data types are used in different columns. For example, a sample might have real values or Boolean values, sometimes categorical and ordinal values. Different distance measures may be required depending on these values. The most commonly used one is Euclidean, but we can also see Manhattan and Minkowski perform similar. Minkowski is the default measure that is used in KNN. Now let's dive deeper into each one of them. First, the simplest, the Euclidean distance. It is the most common measure used in machine learning. In our example, we have a distance between two-dimensional points. It is measured as the direct length between the points. Euclidean distance is calculated as the square root of the sum of the squared differences between the two vectors. I hope it reminded you of Pythagorean theorem, because if we think of this as a triangle, the hypotenuse c square is equal to a square plus b square. In that case, the value of c, which is the Euclidean distance, is equal to square root of a square plus b square. This Euclidean distance also is called L2 norm, if you're familiar with the machine learning term. Now, this Euclidean distance is used when there is a continuous numerical variable in your data set, and you want to calculate the absolute distance between the points. It is important to note that the value have to be normalized before calculating the distance. Otherwise, the distance could be biased towards the higher numerical value. If the scale of variables are not in proportion, then the classification accuracy will be degraded. Hence, it's important to understand the normalization and standardization that may be required in these numerical values or variables. There are some situations, though, where Euclidean distance will fail to identify the similarities, and in those cases, we might want to go for a different function, which is the Manhattan function, the next one is Manhattan function, or the distance. Let's say we want to calculate the same distance between the 2 points, A and B, but this time we want to do a grid-like path. That is, we can either move horizontally or vertically. Now we will be using the Manhattan distance. It is defined as the sum of the absolute differences of the coordinates of the 2 points. This distance metric is used when you're dealing with high dimensional data. It can also be used when you're calculating outliers. This is also called the L1 norm. Now, to understand the difference between Manhattan and Euclidean distance, I came across this example that is really helpful. When we want to talk about the distance between 2 points, A and B, on a map, we mostly think about the distance in a more or less straight line. This can be described as Euclidean distance. But if you want to go from point A to point B, let's say driving, then you would be taking the streets, which says, okay, now how many miles will it take for me to reach from point A to point B? Now this distance, it can be taken as the Manhattan distance. Now that's simple, right? Let's get into calculating these distance. Okay, so here's an example calculation that I made. So we have 2 points, which is employee 1 and employee 2. So let's say we have 2 variables of these people, which is age and pay per hour. So the employee 1, which is the data point 1, has an X value or age of 50 and a Y value or a pay per hour of $180. And then there is an employee 2, who is the data point 2, has an X value of 28 and a Y value of $75. Now, let's try calculating the distance between these two values. As you know, the formula is square root of the sum of squares of the differences between the 2 points. Here we know this is data point 2, which is x2, and this 50 is x1, and $75 is y2, and $180 is y1. And now if we substitute in this formula, we can see that we can reduce it to 107.28. So this is the difference between employee 1 and employee 2 if we plot them in a vector space. The same can be done for Manhattan distance, where you say, okay, take the absolute differences of each of the points and then sum them. So here you can see that it will be 28 minus 50, which are their ages, the difference in their ages, and 75 minus 180, which is the difference in pay per hour. And you can see it reaches 127. Now, if you note that there is a small difference between the Euclidean and Manhattan in this example, but there can be times where the difference is very far apart. In that cases, choosing the right metric is very important. Now for the last metric, which is the Minkowski method or the function. This is the default for KNN model. It is a generalization of the Euclidean distance measure for inputs that have more than 2 dimensionals, let's say Q. So if there are Q dimensionals, then this would be the formula where everything would be raised to a power of Q, and then the root would be taken on that power itself. Minkowski distance is defined as the similarity metric between 2 points in the Q dimensional real space. If we pay attention, we can see that when Q is equal to 2, it transforms into a Euclidean measure, and when Q is equal to 1, it transforms to a Manhattan measure. Minkowski distance is frequently used when the variables of interest are measured in ratio scales. Because it can take into consideration the dimensionality, it is the preferred or the default setting in KNN model. Now, choosing the right distance metric is not an easy task. When we want to make a classification on a data set, the different results could appear using the different distances. So it is very important to be careful in which distance to choose, because we may make a false good artifact that captures well the variability, but actually that might not make sense to our problem at all. Hence, it is important to choose the right metric, and Minkowski proves to provide better results when you're not sure. And now for the last piece to the puzzle is KNN regression. We always think KNN as a classification model, but how many of you knew that it can also be used in regression? That is because KNN model performs well with numerical data. So as you know, the definition of KNN classification is that the prediction class level is determined by voting for the nearest neighbors. But in regression, the average value of the target function value is calculated and is returned as the predicted variable. In this case, the target variable, or y, is always a numerical value. This is one of the main disadvantages that I mentioned earlier again. Categorical variables are treated to become a numerical variable before we can apply it in KNN. Cool. Now we know how to choose the right distance metric and optimize our key. Now let's look at some real world examples. The first one is a fit finder. If you're an online shopper, I'm sure you must have encountered at least a few of these where you input your body parameters like your height and weight, and it tells you your best fit. Most often, what is running in the background is a simple KNN algorithm. It takes into account the previous customer purchases along with their features. It is based on the underlying concept that if you're a customer and you are of height, let's say 5'7", and you got an M size shirt, then it is likely for another customer of similar height to purchase a size M shirt as well. Fit finders are a great application that is incorporated into many online stores, from shoes to gym wears, to give better experience to the users. Another example is a simple recommendation engine. Initially, Netflix and Amazon started having recommendations based on a KNN model. So this is a grid-based measurement where we find users based on what is on their watch list. This similarity is used to recommend new programs when there is a new user incoming. Now, with advancements, Netflix and Amazon have a very big network of models that give you very advanced recommendations. But in the beginning of recommendation engines, it was a simple KNN model. Hence, if you're creating a good recommendation engine as a base, it will always be a KNN model. And the last example in this list is a grocery and retail industry classification, where you classify a customer based on their behavior purchase. This helps the stores to stock up their inventories on new incoming products. All right, now that we know how KNN works and we have seen a few examples, let's dive into the math behind it. So this is a do-it-yourself section where there is a Google Sheet linked. The panelists will share the link in the chat as well for you to click on. Make a copy of the Google Sheet and we will work on solving a simple KNN problem manually. You can also use pen and paper if you prefer that. Before we dive into that, let's look at the use case. What are we going to do? Let's assume you're going to open an online store and you have the height and weight of a few old customers and their shirt size preferences. Now, the company wants you to develop a model to predict the preferred sizes of the new incoming customers. Let's dive in. Please give a thumbs up if you have opened these Google Sheet, are ready to join the next session. Great. Now let's just look at our data set for a second. So you can see that there are about 15 entries of the height and weight of different people along with their shirt size preference here. So there is a few L's and a few S sizes. Now this is a binary classification where you say either the shirt size is S or L. And in the bottom, you can see that there is a new incoming entry where the person is of height 161 and weight 61. Now I'm saying, okay, let's find 3 nearest neighbors here. So the K value is 3. Now we are going to measure the Euclidean distance. We know the formula that Euclidean distance is equal to the square root of the squares of the sum of differences between the 2 points. So here we can say that the height can be taken as x and the weight can be taken as y. So write along with me if you are. So the formula would be is equal to square root of 2 brackets, and we say the first value, which is the x2, minus the second value, which is x1, the whole square, plus the y values, which is this for the new incoming entry, and minus this for the old data point. And then we square that as well. And we close the brackets. And voila, we have the Euclidean distance. Please let me know if you want me to slow down in the chat. But yeah, so this is a simple formula and we now have our Euclidean distance. Now let me just make a change. Yes, so I can repeat it again for you. So the Euclidean distance is this formula, which says the square root of the squares of the, square root of the sum of squares of the differences between 2 points. Okay, so the new incoming entry says that this is the height of a new person and this is the weight. So we consider height to be x and weight to be y. And we have these old data points and we are trying to measure the distance between this particular data point and this particular new entry. So we say the Euclidean distance is square root of the first point, which is x2, that is the height, minus the second point, which is x1, the height of the old point, plus the y2, which is 61, minus 58, the whole square. And once you have this entered in your formula box, press enter to get your Euclidean distance. Now, important thing to note is that the F19 and G19 columns have to stay the same as we calculate distance for all. So let's add a, oops, I'm sorry, give me a second, please. Yeah, sorry about that. Can you all see my screen just to confirm? Yes, perfect. Thank you. So you can see that we have calculated for one. Now we just want to make sure that these ones, the F19 and G19 columns stay the same while we calculate the distance for all other points. So simply click them and drag to fill the other distances. Perfect. Now we have the distance for everything. Now what I'm going to do is sort the Euclidean distance from smaller to bigger number. So you can see that this has the smallest relation, so smallest distance or more similarity towards this value. And the Euclidean distance is 1.4. Now we have this arranged. And let's say our K value is 3. So which means we take into consideration the first three neighbors. So there are two S's and one L's, which suggests that our prediction would be a small. In a similar fashion, let's say if we assume that the K value is 7 for the same entries. Now we have to consider 7 data points. So now if we count the number of S and L, there is 1, 2, 3, 4 S's and 1, 2, 3 L's. Again, because of majority voting, S gets precedence and we can classify the second one as small too. Now I have a small homework for you, or if you can take 2 minutes to do this. Let's say there is a new person incoming who has a height of 165 and a weight of 66. Let's take 2 minutes to calculate what would be the predicted size given that the K value is 5. Please take 2 minutes and try it out, and I'll share the results after. And if you got answers, you can share it in the chat for us to see. Raquel has the answers, all large. That is right, Raquel. And Liz has another question in the chat, which says, if there is no M in the original data, it seems like we are confined to only seeing S and L. Yes, Liz, I tried having this as a binary classification just to ease up the classification prediction manually. Shubi has answer L. Yes, you guys are right. The answer is L. So let me just erase it just to show you guys what the answer would be. So I'm inputting the formula, which states that, okay, take these 2 points along with the old data points as X and Y values and calculate the answer for me. And we are going to expand it to all the values. And then we will be sorting from the smallest distance to largest. And we'll be looking at 5K values. So the first 5 states that everything is L. Well done, everybody, and you did a great job. Now let's get back to the presentation. Now, this was a very simple algorithm, right? Like easy to implement, easy to explain when someone asks you. That is the power that makes it a more preferred algorithm in the industry. Though it is simple, it is really powerful. And now let's take a 5-minute break before we continue with the coding part of the session. And in that 5 minutes, for some of you who are having error in their formulas, let me go back to show you the formula here, just for you guys to copy or try it out. All right, welcome back, guys. Let's start this session again, the second part, which is the Google Colab Notebook. The link has been shared already in the chat section. You can click on that to open a notebook. So basically the link is to a GitHub page. Click on that and open your GitHub page, and then can you all give a thumbs up to say if you're ready for the session? so that I can go ahead and show you the instructions of how to do it. Perfect. Thank you. So yes, so we have a link in this page, which links to your GitHub page of Women Who Code. You can have that open here. And once you have that, go to Google search and type in Google Colab. You will have this page open. You can click on this link, or you can go to collab.research.google.com. Once you click on that, you will have this page pop up which says, okay, enter the link. So enter your GitHub link in here. And once you press enter, you will see that the Women Who Code data science repository is filled. And click on the first one, which is says K nearest neighbors in advanced machine learning. So it's intro to ML, sorry, intro to advanced ML, knn.ipynb. So once you click on that, you will have loaded the notebook into your Google Colab environment. Once you're done with that, next is the part of data. The data that I'm using here today is a data set that contains all the Google Play Store app data, and it can be found in Kaggle. I'm sure our panelists have shared that link as well. So go to kaggle.com, follow the link to go to kaggle.com and go down to the Data Explorer where you can see this button to download the Google Play Store.csv. Click on it to download, unzip it, and once you are done with that, go back to your notebook, and on the left side, you will have this file icon that you can use and do an upload to the storage. And you can click on the unzipped file, which would be a CSV, and open it in this environment. So this is a temporary folder that will be used to process the document on this side. Please let me know when you've reached this step. I can repeat if you need any more guidance. Our panelists are also there to help you. Okay, I can repeat this again. So there's a link in the presentation that links to the GitHub page, which is this. So you need two links. The first is this GitHub page, which shows the notebook, K nearest neighbors. And then you have to open search, Google search, and type in Google Colab. So the first link is to their Google Colab environment. Click on that to open your new environment. And in that, in the top tab, you can see GitHub. So click on that and enter the GitHub link that was provided by Women Who Code. Oh, in the chat, sorry. It's available in the chat. It's available in the presentation. It's a GitHub link. Yes. So once you have that, press enter, and it will load all the Python notebook in the repository. And we want to be loading the first one, which says Intro to Advanced Machine Learning, knn.ipynb. And when you click on that, the notebook would be loaded. Are you done with this step? Please let me know in the comment, the chat with the thumbs up. Perfect. Yes, next is the Kaggle step. So the link would again be shared. let me share the link again so that it's easier. So this is the link to the Kaggle. It will lead you to this page where there is a data set on Google Play Store apps. Yes. Once you have that, if you go down to the Data Explorer, you can find this button, which is download. So you can download that, and it downloads a zipped file. You can unzip it and you will find a Google Play Store.csv file. Were you able to locate it in Kaggle and download it? Please give a thumbs up. Yes, perfect. Thank you. So once that is done, we go here to our Google Colab notebook and we click on this icon in the left tab, which says files. And once you click on that, it is going to connect you to the environment. And after connecting, there is going to be this first icon, which says upload to session storage. You click on that and you will have your unzipped file here, which is Google Play Store.csv. Click on that and open, and it will give you a reminder that says this will be deleted after the runtime. That's okay. Press on OK and you will have it downloaded here. Is everyone getting a success message? Is your data loaded in? Perfect. Thank you. Right. So once you have that, you should be able to follow along with the presentation. Okay. So the first thing is okay. So everyone has set up. I have so many thumbs up in the chat section. So I'm going to move on to the next part, which is the presentation itself. We have the Google Colab notebook. We have the CSV file here ready. And today in this session, what we are going to do is we are going to build a k-nearest neighbors model to predict the rating. Sorry for the typo. To predict the rating of an app based on the user experience. So if you remember seeing the data, it is a Play Store apps data, which talks about how the app performed basically. And we have completed the setup and importing data part of this session. Let's go next to the data cleaning and feature analysis. After that, we will generate the model, and then we will do hyperparameter tuning, where we'll find the optimal K value. There are a few fun stuffs in the end as well on how to implement grid search. If you don't know about it, it's a very cool feature to find the optimal values without putting in a lot of effort. Yeah, so let's start. And before that, a brief introduction. We know KNN in K nearest neighbors, the K denotes the nearest neighbors, and we use the distance metrics to measure the distance between 2 points. We start by loading the base packages. Here, NumPy and Pandas are our base packages, and then I'm using Plotly, Seaborn, and Matplotlib, which are plotting the graphs. And then we use sklearn as our base package for loading our machine learning model. As you know, sklearn is one of the opted packages in the machine learning platform. Next would be about the data set. So this is a very interesting data set that I came across. The Play Store app data is, for me, was important because if you're an app developer, you can look at this data to see what are the best ways to develop an app that would capture the Android market. So we can derive so many actionable insights from this. Here, what we are going to do is look at the features and see how the rating is for these apps. And this will help you in deciding if you're entering the Android market. So first thing is a very simple read CSV command, which loads your data frame, which loads the file into your data frame. And after that, I have done some pre-processing or data cleaning. So if you remember, it is important to have a very highly accurate data to have your model perform well. So what I'm doing here is making sure that my data is complete. So I am doing a bunch of things here. I'll try going over it in a good way. So what I did here is I'm taking the content rating that is for everyone. And there were some categories or rating which are not used by a lot of apps. So I'm just doing this. And then I'm saying, okay, if there's a size, let's take the sizes only in MBs. So because there are some which are in kilobytes, KBs, and GBs, and we want, I'm doing this just to clean up the data. Getting the size value without the M to make it a numerical value. And I am taking the apps that has at least 500 downloads in the Android versions they have mentioned, and at least 100 downloads in the category they have mentioned. For example, if there is a category called houseflies, nobody wants that category, and we don't want to worry about that category. We want to take the categories that are popular. So I'm taking any category, I'm only taking the categories that have more than 100 downloads. And then I'm rounding the rating to say that we are only trying to classify between 5 values, which will be 1 rating, 2, 3, 4, and 5. And some more processing. And this is how your final file would look like. You can see that these are the important categories that I'll be using. So these features I chose because I think they are important. It could be different for you, and you can process the data that would fit your requirement. And hence this is, yes. So to look at this data, we can see that there is this field called app, which shows the name of the app. And then there are categories. The main category or the top category seems to be book and reference. Reviews are the number of reviews written by customers. The size is the size of the app itself. As you know, I did pre-processing to change a categorical variable into a numerical variable. I did the same with installs, and here installs are in thousands and 100,000s. Then there is a genre and the Android version that the app is supporting. Usually you want the Android versions to be the newer ones. So that's how you know that the app is keeping up with the market. And then the rating. And rating is the Y variable or our target variable that we'll be using to find, to do the prediction. And here is a good way to look at the data. It's df.info. So you can see here that there are 3,512 entries. And when you see, okay, we can see what are the non-null counts in the data. And you can see in ratings, we only have 3,080, which means about 500 of the entries are nulls. And remember that you need highly accurate data, and this can lower the prediction. So what I'm going to do is I'm going to drop all the NAs. So dropping the NAs, and I'm checking, okay, now how much entries do I have? And there are 3,080 rows, which is not bad. because 3000 is still a good number to give a good prediction. And we have seen the features and we have made some data cleaning. Now let's look at the features. One thing you should know is that the KNN doesn't take into consideration the distribution of the variables. Hence, we don't have to worry about if the data is normally distributed. And for that reason, it is also called lazy classification or lazy learning algorithm. So all we are going to do here is just to see how the data is, just to understand if the data is of high quality. The first is a small distribution plot, which is based on the size. You can see that the majority of the apps are within 20 MB of data, which is expected. Nobody wants a heavy sized app that would lag your phone unless it's for gaming. And the next plot here shows the installs. You can see that there are about 1 million installs, are like there are about 500 apps on million installs, and the lowest being the apps in hundreds and 500s. This states that if there's more installs, then probably So this is just to show you the distribution of the installs and how many of the apps fall in each category. And you can see this is the category that is more famous, or most of the installs are happening in this category. And then we look at the reviews separately. So how many reviews are present for each install? So let's say 5 million. So if the install is for 5 million, how is the distribution of reviews? And you can see that 50,000 is the nominal review, number of reviews for the install that has 5 million downloads, which tells me that only 10% to 15% of the users actually rate their apps. And the same to see, okay, is there a connection between rating and the size? And you can see that there are very less apps that are of the rating 1, and most of the apps are rated 4-star, which is meaningful because most of the apps that we see are always 4 stars. It's so hard to find an app that will not perform well. They kind of die soon. And you can see that the size is basically less than 20 MB. And if the size is more than 20 MB, they mostly fall under the category of 4, the rating 4. And lastly, we are going to see if there is any connection between the installs and the rating. And you can see here that the rating increases, the 4-star rating increases with the number of installs. So the more your install tells you that the app is good, that a lot of people are installing it. We are not, oh, there's one more plot, which is on the rating and the size, which is similar to this, but in a different style. This is to show you that this is a very biased data set, as in there are a lot of outliers, but these outliers are not going to skew the model because the KNN does not care about the distribution of the data. It cares about highly accurate data, and because of the pre-processing, our data is highly accurate right now. And yes, so as you know, these are the variables. So we will be using the category, reviews, size, installs, the genres, and the Android version to see what the rating of that app would be. And you know that these are categorical variables, for example, the category and genre and Android version. So we need a way to transform these categorical variables into numerical variables. We do that using label encoder. And you can see here that I am fitting, so I'm calling the label encoder function. It is part of the sklearn pre-processing package. And once I call that function as my label encoder, I'm saying, okay, fit transform for the genre, the Android version, and category. And if you look at the head of the data frame again, you can see that all my categories are changed into numerical values. All my Android versions are changed into numerical values. And the genres are again converted into numerical values. Now we are ready to train our model. Yes. So again, let's say that we are interested in rating. That is, rating is our target variable, and all the rest of the things would go into our X, which is the independent variables. You can see that we are going to let go of app because it's just a name and they have no relevance to how a rating occurs. So here is where I am making the differentiation of what are my X variables and what are my Y variables. And you can see that category, review, size, genre, and Android version are the variables that are X that I will use to determine the rating, which is the Y. And here you can see that I am converting the rating into a type string. This is because I want to have them as 5 classic values of 1, 2, 3, 4, and 5. Now let's look. So this is how you convert them into NumPy arrays. And now we can see, okay, what is the shape of these arrays? So we can see that there are 3080 values available, which each has 5 different features. And the Y has, again, the same length, which is 3080 with no features, because that is the variable that we'll be predicting. And here I'm using the train test split to split my X and Y variable into a train test and a test set. So here I'm saying, okay, I want 80% of my data to be in the training data set, and I want 20% of my data to be in the testing data set. So the random state is just a number to make sure that you can repeat the experiment. And yes, once I run that, I'm checking how much is the split. So of the 3080 rows, 2464 was made into training data set, and 616 rows are made into testing data set. Cool. Now we have the data set ready. Let's see what are the important packages that we need to install before we create our model. So sklearn.neighbors has this package called kneighbor classifier. That is the ML model itself. And we need some metrics to see how well our model is performing. And then I'm also getting a confusion matrix, which will show you if the classification of the prediction and the test are the same. This is good to visualize how well your model is performing. And here is a classifier which says, okay, create me a k-neighbor classifier with number of neighbors equal to 2. So this is your k value. I chose 2 just to show you that how good can an arbitrary number function. And then I'm saying, okay, fit the model, which says X train and Y train. X train is the independent variables, and Y-train would be the dependent variables. And once I run that, it shows you, okay, hey, I have created this K neighbor classifier, and these are the hyperparameters that I'm using. The first thing is algorithm, which is not really important unless you want to really fine tune it. So we are not going to talk about it. And it's the same with leaf size, metric params, n jobs, p, and weights. The main two parameters here that we will be thinking are Minkowski metric, sorry, the distance metric, which is Minkowski, and the n neighbors, which is 2. So these are the two parameters we talked about in the presentation, where we said, okay, hey, you need to optimize your K value and you have to find the right distance metric for your problem. So in default, the metric that will be used to measure the distance is Minkowski. Cool. Now we have trained our model. Now it's time to get the predictions from it. So here is a method that says ypred, which is my prediction, is equal to classifier.predict my test set. So which is the x underscore test. And then I'm saying, okay, get the accuracy score based on the prediction and the test answers are the predictions. And here you can see the accuracy of the model came to be 58.3%, which is not bad because this is our base and now we'll be building on it, tuning the parameters to get the best model out of KNN. And here is a very simple plot on the confusion matrix. You can see that 3 performs well, which is actually rating 4. So you can see here that 0 to 4 shows the rating, which says it is 1, 2, 3, 4, and 5. So 4 rating is the one that performs well. This makes sense because we have so many values in the rating 4. And the next one that is performing well would be this, right? Yes, where the rating 5 is predicted as rating 5. Most of the rating for 5 is, most of the rating for 5 is predicted as 4 here. So this is something we want to see and reduce. So in this problem, I am looking at accuracy as my important metric, but it doesn't have to be the same. You can also consider other metrics like precision, recall, F1 score, and accuracy, accuracy as well. To give you a small definition or understanding of how these things work, accuracy is the most intuitive performance measure because it's in the name. It is a simple ratio of correctly predicted observations to the total observations. You might think if you have high accuracy that your model is best, but actually the accuracy can be trusted only when your data is symmetric. Here for this example, we follow accuracy, but you have to look at other parameters to evaluate the performance if you are going to deploy this model in a larger scale. The other metrics, one is precision. It is a good metric when you want to have your false positives to be low. For instance, let's take an email spam detection algorithm that's based on KNN. And in email spam, a false positive means that an email is classified as spam while it is not a spam, which means the user is losing an important email. So you want the precision to be as high as possible to make sure this error doesn't happen. In the similarly, recall is used when you want to have true positives. That is, let's take an example of fraud detection. So if a fraudulent transaction, which is happening, is predicted as a non-fraudulent, which means it is predicted negative, but is an actual positive, the consequence can be very bad for the banks. Hence, you want to make sure in those cases, in fraud detection or outlier detection, you want the recall score to be as high as possible. And when you don't know what to choose, like should you be choosing precision or recall or even accuracy, F1 score is always a safe way to, is always a safe metric to go to, because uh, because it shows a balance between precision and recall. But here, for the sake of demonstration, I'll be focusing only on accuracy. Also because it is a classification model. And we got 58% accuracy, which is not bad at all. Now let's try improving the model. Okay, so there are two parameters again, I told you that we have to optimize: the K value and the distance metric. Let's start with the K value. What I'm doing here is I'm trying to get the accuracy for every model that I'm going to be creating. So here it is a for loop which says for n neighbors, which is a range of 1 to 30. So from 1 to 30 neighbors, calculate my, fit my model with the n neighbors, and then make a prediction and tell me how much is the accuracy. So basically what this does is it runs a for loop for each n neighbor starting from 1 to 30 and tells you what is the accuracy for each. So once you run that, I'm going to use this method, which is a very nice interactive plot for us to look at. So here is the accuracy versus K. So you can see that when K is equal to 1, the accuracy is at 60%. And then it drops to 58%. And if you remember, we used in our first model K as 2. That states that, okay, 2 performs so bad. And then it starts increasing over time, and it reaches its maximum accuracy at 68% when K is equal to 21. Now that is our optimum K that we will want to use. Now let's test this. Now let's create a model that says, okay, hey, I want the K nearest neighbor model with n neighbors is equal to 21. I train, again, fit the model with the training data set and then make the prediction with the test data set. And you can see that the accuracy has improved by 10 to 11% because this is 68%. So exactly 10%. So the accuracy has increased from, if you see here, yeah, 58% to 68%, which is a 10% leap. In real world examples, these kind of accuracy improvement is phenomenal because it shows that your model is performing way better. And if you look at the data, you can see that this area and this area classification has reduced, that the number of classifications in rating 4, which was about 271 in the previous confusion metrics, has become 395, stating that the prediction power has increased because we changed the n neighbors from 2 to 21. Now this is good, right? Now we have done the hyperparameter tuning for K. But how about the other metrics? We see so many metrics here in KNN model. How do we know which is the optimal value to use for all the other metrics that I mentioned before. We don't have, as a beginner, you would not know about all the metrics that are present in a model. So that's where I found this cool package, which is model selection, which shows you, which has this thing called grid search CV. So what it basically does is you can say, hey, these are the parameters I have. I have n neighbors, I have the distance metric, but I also want to, these are the two things I know, but I also want to see what is the leaf size that would be perfect for my model, or what is the weights and the algorithm that would be perfect for my model. I have no idea on how that is done. And this method gives you the output based on the metric that you mentioned. So here I'm saying that, hey, the model is K neighbor classifier again. And I'm saying, okay, these are the parameters that I want to set and test. So I'm saying, okay, I want my n neighbors to range from 1 to 30 values. And the leaf size, I want it between 1 and 5. And the weights, there are only two options for weights, which is uniform and distance. These are advanced metrics that are used and that is outside of the scope of this presentation. But I have linked some links in the presentation slides for you to just go and check it out. You can learn from those. The next one is metric. As we mentioned, there can be three metrics, which is Minkowski, Manhattan, and Euclidean. And then the algorithm. This again is out of scope for this presentation, but I have a link that talks about this as well. And here I have four options, which says it's auto, ball tree, KD tree, or brute force, or brute. And I'm saying, okay, use the grid search V, and this is my model, which is from here. And these are my parameter grids, which says, okay, this is the dictionary of parameters that I want to pass to this model. N jobs is another hyperparameter, and it's useful when you're doing parallel computing. Usually when you're running a single computer, you would probably not want this parameter. So I'm saying, okay, so this is now my model, which is model 1. And I'm saying, okay, now I fit the X train and Y train, which is, I'm training the model, which is a grid search model right now. And then I'm saying, okay, once that training is done, choose the best hyperparameters for me and print them for me. And then do the prediction and print the score for me, which is the maximum score for that model. And then I have a confusion matrix as well. So you can see here, it shows the grid search. What it does is, remember the for loop that I had before? It basically does this, but it does it internally for us. We don't have to write this many codes of a for loop. So it says, okay, I went through all the processing for you, and this is the best hyperparameters that I figured. So it says the algorithm auto performs well, and the leaf size is 1. And the metric, remember we had Minkowski. It says Manhattan is the good metric that you should use. And it says, okay, the number of neighbors is 29. So remember we saw that at 21, the accuracy is at its peak, but that is beaten here again, that it says the K has to be 29 and the metric has to be Manhattan, which are the true metrics that we looked at. And it says the weight has to be distance. And it was able to give us a prediction of 69.6%, which is a 2% jump from our previous model, which is 68%, which is still good because we are tuning everything. So one by one, we are trying to make the model better for us to use and deploy if necessary. Now I'm looking at a sample of the data set, and you can see that, so these are the predictions, the first row, and the second row is the real values of the data. Oops, I'm so sorry. Let's go here. Right. So you can see here that a 5 is predicted as 5, so that's right. And the next one is a 5, but it's predicted as 4. So there is some issues there. But then you know the model is only 70% accurate, which means we know that some test values are going to be predicted wrong. And you can see here there are a few 5s that are predicted as 4s, and there are a few 4s that are predicted as 5s. But this is understandable. And now that in an overall score, we were able to increase the accuracy from 58% to 70%. Using optimizing the k-value method and the grid search method. The next step on this would be to further improve the accuracy. How can we do that? So there are a few methods that you can try to improve upon this model. So the first one is hyperparameter tuning. The grid search CV did do a good job of tuning the parameters for you. But you can also look at how every changes impact by employing each of the parameters and looking at the accuracy, and also maybe look at the F1 score and see how the change happens. Like sometimes the rating 4 can be predicted as 5 more, and sometimes it can be vice versa, which suggests that you need to look at precision, recall, and the F1 score as well to see how good your model is performing. The other way to increase accuracy is feature engineering. So initially you saw me doing a few steps that helped in manipulating and selecting the data. But there are bigger things than that, as in principal component analysis to find, and also like domain knowledge to find the features that will help you with predicting a better rating. For example, in this example itself, I have dropped a few columns just to make this shorter. But if you look at this, the category and genre are highly correlated, as in they both have book and reference as their category and genre. So this, it feels like it is highly correlated. So through feature engineering, I can say, okay, I'm going to drop the category and have genre as my only column to process the data. And this will in turn help you with accuracy. While this is an example, you can look at other ways of doing feature engineering. Our previous introduction to ML sessions have a very good video on that, if you guys want to look at that. And the last way to optimize your accuracy is optimize your model or increase your accuracy is to try other models. There are so many classification methods out there. And better yet, try combining models. So it's a very nice ensemble method that was taught by Sumana in our previous webinars. The link is not here. It is there in our Slack community, and I encourage you guys to join our Slack community to see what are recent events and anything that's happening, and exciting content as well. Okay, so now we have our perfect fit of a model, which gives an accuracy of 70%. What's next? So the next thing for you is, this is a data set of 9,000 columns, so now 9,000 rows. I made it into a small subset of 3000 rows just to give a demonstration of how the KNN model works. Now you can go back to the data and see what are the data manipulation and data pre-processing that I've done, and choose to capture different features or eliminate different features and rerun the process again. See how the model reacts in terms of accuracy, and see how the grid search CV gives out different hyperparameters when you change the feature that you're inputting. So the one way is to play with the Google Colab notebook itself. It's a good way to get started. And then I would also like to point you to usual practice data sets. The two data sets that are used in KNN usually are the IRIS data set and the MNIST data set. IRIS data set is very beginner friendly, and we have so many tutorials on that available on the internet. You can just go ahead and see how that is being processed. And then the last one is MNIST data set. It is one of the interesting data sets for me because it is image recognition or image pattern recognition. So you would not think a classification method being involved in classifying images, but KNN is simple yet such powerful algorithm that it actually gives good prediction results for that data set. And yes, I encourage you to look at that data set as well. And that can be your next project. Yes, with that, we come to an end of this presentation. Please let me know if you have any questions, and you can also connect with me on LinkedIn and Slack. To finish off, I just want to go back to the presentation and tie everything together. So I have listed here in the slides a few of the resources that you can use to go further in the KNN model. The first one is an official document. I think it's really important for you to look at an official document when you're trying to play around in a new package. The other one is a medium example of another good data set being solved for KNN. And then the last one is get in depth into hyperparameter tuning, where it talks about all the other hyperparameters that we didn't take into consideration in this session. So apart from the K value and the distance metrics, all the other metrics or the hyperparameters are also discussed in this article, which I found it to be interesting. And yes, we talked about these two data sets that you can try, and it could be your GitHub project, and you can share it with us in Slack and tag us in social media, and we would be very happy to look at. And if you would like to review, we can also do that. That's about it. Thank you all for joining today's session and taking your time off on your weekend to learn these concepts. If you have any questions, again, join us on our Slack community and post your questions to us through any of the social media handles. Our panelists will be sharing that link as well in the chat. And yes, we look forward to seeing you all next week when Funke and Aryan would be covering the concepts on clustering. That said, thank you all once again for taking your time on a weekend. Bye-bye.